Salam and a very good afternoon to everyone. I am Dr. Akila from UPNM, along with co-author Dr. Azali from UMS. We'll be presenting our paper entitled Rotated TOR-5P Laplacian Iterative Path Navigation for Obstacle Avoidance in Stationary Indoor Simulation. The agenda for today covering 5 main topics, which are introduction, some related studies, method that will be used, results from simulation, and finally, the conclusions. The movement for humans are extremely trivial. It is a very simple task for us to move from one room to another without hitting the walls or any furniture. Whereas the movement for a robot can be considered a central problem. Every movement requires precise computation, even for an inch. With the latest issue of pandemic COVID-19, the studies on robotics are a crucial study nowadays. What is actually robotic pathfinding? It is a navigation or movement of the robot from departure point to the destination autonomously while avoiding all of the obstacles in between. How we define a good pathfinding algorithm? It will be said good if it provides minimal cost of computing, having optimal time taken, and eventually able to reach the destination in the most efficient manner. In related studies, for these works, we divide into 4 categories, which are global Laplace's potential method, harmonic functions, the half-sweep approach, and the two-parameter of relaxation iterative method. This is some of the works that has been implemented previously based on these 4 categories. For method, we'll start with the half-sweep TOR. It is a numerical approach in solving the problem for this study. It is actually the generalization from AOR method and under the family of over-relaxation iterative method. We will be using global approach instead of local because it recognizes the map. In the map or the environment, the path is constructed before the robot starts its mobilization. How the path is constructed? The movement of the path is based on the heat transfer analogy, where the heat will flow from region of high temperature to the lowest temperature. And what equation we refer to for the heat temperature? Laplace's equation is used to obtain the temperature distribution in the configuration space, whereas the harmonic function is the solution to Laplace's equations, are capable in providing prompt and efficient solution to Laplace's equation. How the path is constructed using heat transfer analogy? Let me show you with some figure. By using 2D robot simulator, we firstly assign the high temperature value to boundary walls and obstacles as heat sources, while the goal point as heat sink that pulling the heat, assigned as lowest temperature. During a heat transfer cycle, the temperature diffusion reflecting the values of Laplacian potential fill the configuration spaces, evolving and flowing from heat flux lines into the sink. It is easier to see the path through the heat stream. This cycle assures a path towards the goal minus facing local minima and positively escaping the barriers as discovered by Connelly in 1990. We can describe the C space or configuration space in nodal points, where we'll consider to calculate all knots for full sweep and only half of the knots for half sweep in the mesh points as shown. For the computational molecule of full sweep and half sweep, the h and set through h is the distance between knot points in each direction. There are 4 different environments considered in this study. From these figures, the black area indicate walls and obstacles, whereas the white color is free space for the robot to move around. Next, we'll go to the formulation. First, we'll consider the Laplace equation on domain O. From this, we form a 2D Laplace equation. The discretization of Laplace equation is based on rotated 5-point second order finite difference approximations. This scheme will be implemented to half-sweep SOR method, which have one parameter omega. From here, to improve the results, we apply AOR method that has 2 different parameters, R and omega. The AOR method is basically the generalization of SOR method. And finally, to boost up the results, we generate TOR method in which has 3 parameters, R prime, and omega. By using all of this formulation, we will execute the pathfinding in 2D robot simulator. For environment 1, as you can see from the figures, the green dot is actually a starting point, while the red dot is the target. You can allocate the start and target point anywhere in the free spaces of the environment. From the simulation figures here, the paths are successfully generated from starting to destination without bumping the walls or obstacles, even though there are tiny spaces. The same thing happened to environment 2, environment 3, and environment 4, where the smooth path is successfully generated. We can say it's smooth because there is no jagged line compared to previous studies. For comparison purposes, the bar chart for both iteration counts and the time taken based on results are built. For all environments, the HSTOR shows the best correlation where it needs smaller number to iterate compared to other methods. The results also prove that HSTOR took less time comparing other methods in order to complete the path. In conclusion, we can say HSTOR is the superior pathfinding performance proven by the shown results, which require lower iteration number to complete computation as well as execution time. The number of obstacles does not adversely influence the results. Instead, the computing gets faster as obstacles regions are ignored during calculation. We can say that further discretization of SOR and AOR indeed improve path planning algorithm performance. In terms of the advantage of developed algorithm, complete algorithm is guaranteed to find a solution path if it exists. As for future works, the implementation of quarter sweep technique can be considered to reduce complexity and boost up the computation. Thank you.